Hey Royals, for lesson 6.5 on geometric series, let's develop the formula and take a run through one of the trickier examples where we have some more work to do. Geometric series, if you're planning on continuing in mathematics, maybe you're interested in calculus, it's a very important formula. You won't use it in high school calculus, but it's really, really useful for adding up an infinite number of infinitesimally small things. If you're interested in finance, and unfortunately we won't have time to do our finance unit this time through, but when you're working with finance, when you have an annuity, when you have a series of regular payments into an account that's gaining compound interest, your future value turns out to be the sum of a geometric series. So you'll see different unknowns used in a finance situation, but it is by far the most useful formula, and maybe the most applicable formula in our entire course. Yeah, so it's worth a look. Okay, our task is to find the sum of a geometric series with term 1, term 2, term 3, all the way up to term n. Well, since this is a sequence, we can find the first term as being a, and since this sequence is geometric, we will have a common ratio. Let's review that the second term is going to only have one factor of r, because the first term has 0 factors of r. The third term will have 2 factors of r, that's 3 minus 1. That means let's go to this nth term here, because that's our formula for the general term of a geometric sequence. It will have a times r to the exponent n minus 1, only n minus 1 multiplications of r. This is term 1, term 2, term 3, that's term n right there. That means the term before this is going to have one less factor of r than n minus 1. 1 less than n minus 1 is n minus 2. Okay. Notice the exponents on r increased by 1. Okay, Gauss's method of reversing isn't quite going to work out here. Our first plus our last isn't actually even like terms, and it's not going to be the same as our second plus our second last. So what we do instead is we try to come up with a way of building a ton of like terms. And we do that in a weird way by multiplying this sum by r. So multiply this sum by r, and you can use the distributive property. You're going to multiply every single one of these terms by r. A multiplied by r will be a times r. A times r multiplied by r will be a times r, also known as ar squared. Basically, I don't like using the word adding because I'm not adding, but I am placing one more factor of r in each term. So I am multiplying by one more factor of r. There is an addition happening in the exponent, but I'm not, I don't want to say I'm adding a factor of r. I could use it if I was in an English class, but I'm not. So there used to be n minus 2 factors of r. There is now one more than n minus 2 factors of r. One more than n minus 2 is n minus 1. And over here, there's going to be one more factor of r. You can do your grade 9 power laws if you like. R to the exponent n minus 1 multiplied by r to the exponent 1 is going to be r to the exponent n minus 1 plus 1, which is r to the exponent n plus 0, also known as n. But I think it's probably better for you to reason it out. So how is this useful? Well, let's take a look here that those two terms are like terms. In fact, they're identical. And those two terms are identical. And I didn't write it, but I'm sure you can trust me that there will be an AR cubed term right there. And I didn't write this term's partner, but there before this AR to the exponent n minus 1, there will be an AR to the exponent n minus 2 term there. And those terms are identical. So we can simplify eliminating a lot of these terms through subtraction. So what we're going to do, we'll call this statement equation number 1 and statement equation number 2. We're not eliminating one of the unknowns or any of the unknowns. We're eliminating a very large number of terms. I suppose we're eliminating n minus 2 terms, I think. Not important. So on my left-hand side, let's not forget about my left-hand side, I'm going to have r times s sub n minus s sub n. And that seems kind of unfortunate because that's not what I'm trying to find out. I'm trying to find the sum. We'll deal with that in a sec. And then watch what happens here. Oh, now watch what happens here. I'm doing the second minus the first just to keep things positive, let's say. So I'll have this term right here doesn't have a partner. It is not being subtracted by anything else. So I'll start with it. And then I'll have this term minus that term. Well, that's 0. And this term minus that term, that's 0. And this term minus that term, that's 0. And that's 0. And that's 0. And then the other term that doesn't have a partner is this a. It's going to be subtracted. So it's like these two oddball terms that don't have partners just to decide to partner up there and be subtracted. Okay. And that takes a sequence that could have millions of terms and breaks down an expression for its sum down to 2 terms. Now, my goal on the left-hand side is to isolate for S sub n, but there's more than one instance of S sub n. We're going to use a skill that we have used many times in this course. We are going to remove a common factor. The alternative is you think of this as like terms. If I have r S sub n's and you subtract 1 S sub n from me, won't I have 1 less than r S sub n's? Just make sure you don't think that r S sub n minus S sub n is r. That's like saying 5x minus 1x is 5. It's an easy mistake to make in grade 9 if you think that you're removing the x, but grade 9 students learn that this means 1x. It's an invisible coefficient. Don't do that. Sorry. Okay. Since we common factored on the left-hand side, why don't we common factor on the right-hand side too? I know it's a weak argument, but it kind of makes things just a little bit more recognizable. So I remove a factor of a from a times r to the exponent n. That leaves me with r to the exponent n. I remove a factor of a from negative a. That leaves me with a quotient of -1. And I'm one step away from isolating for S sub n. I divide both sides by r minus 1. Notice the restriction on this rational expression. My denominator can't equal 0. That means that my common ratio can't be 1. If I'm using this formula to find the sum of a geometric series where the common ratio is 1, I'm demonstrating a very large lapse in understanding. Okay. Think about that sentence and see if you can figure out why that's kind of an issue. So here we go. There is your formula for the sum of a geometric series. Normally, when we do a Unit 7 and we talk about finance, we see this formula come up so often that we just plain end up memorizing this one. The development I don't expect you to be able to do, but it is, again, nice to know. In a traditional situation where we have a final exam, this formula wouldn't just be given to you because you can figure out this formula and you should be able to walk through this development. Maybe not come up with the idea yourself the first time. I didn't do that. I'm not sure who did it. It wasn't Gauss. But yeah, it's not that hard to do. There are some issues with typing things into the calculator here. We need to be very careful with our brackets. In fact, let's just go ahead and put brackets around the denominator. They're not required there when I write this formula out. But if I'm going to pick up my calculator and type something in, I'll probably either just want to do this operation in my head. Maybe I don't need a calculator to do. Let's say I have a common ratio of 2. Maybe I don't need a calculator to do 2 minus 1. Hopefully I'm not so dependent on my calculator that I would do that. But if I have a common ratio like 1/3, I don't know, even then maybe I should just do -2/3 down there. I don't know. Use brackets if you have to. Okay, let's try out, I'm not sure if it's a numbered example, but let's just try out one of the examples from the lesson. Let's find the sum of -6 plus 24 minus 96 plus ... plus 98,304. Again, we should be able to do this efficiently. We shouldn't have to list out all the numbers, continuing with this pattern, and then type all of those numbers into our calculator. That's not an efficient approach. This is where in a traditional classroom setting, we would have a time limit on a test. And it's a sore point because some people work faster than others, but sometimes people say, I need more time to do this question, and I look at their page and it's because they're listing all the numbers out. And I tell them, no, you don't. Right. Let's see. The other thing to keep in mind is that we're doing our homework day by day, hopefully. So you will be concentrating on geometric series when you're looking at lesson 6.5. But on a test or a quiz or an exam situation, there's nothing that's going to tell you that this is geometric. This is why it's really important for you to sort of show your work to convince your reader that it is geometric if it doesn't say so in the problem. So, I notice an alternating sequence here, which I've seen with recursive sequences, but we didn't talk about the sum of recursive sequences, purely recursive sequences. So my gut is telling me that it is geometric. I also see that it doesn't look like there's a common difference. So let me tell my reader I'm doing T3 divided by T2, show my reader that that's 96 divided by 24, and help my reader see that that is -4. Let's convince my reader that term 2 divided by term 1, which is 24 divided by -6, is also -4, and then we can conclude. When you write r equals -4, you are saying this is a geometric sequence with a common ratio of -4. I guess let's get the value of a out of the way. A is also given. It's -6. Notice to find the sum of a geometric series, we need to know how many terms there are. So I'm not ready to use this formula yet. Go ahead and treat it like a checkbox. You're looking for S sub n, but you don't even know what n is. I know A, I know R, I don't know n. What I do know is the nth term. And I do know a formula for the nth term, or I can build a formula for the nth term of a geometric sequence. The first term is a, the second term is a times r. The third term has 3 minus 1 factors of r. The nth term is going to have n minus 1 factors of r. So be careful with how you show this work, because sometimes students start with this equation and then they go off to the right and they do work later. And then when you read a solution from left to right, it looks like these numbers showed up out of nowhere. I don't expect you to look 5 steps ahead and figure out exactly how you're going to solve this problem. But when you get here, pause and say, oh, I realize I need to use this number to help me solve the problem. Into this equation, we will substitute 98,304 for T sub n. -6 for a. Let's use brackets. They are required here to show the multiplication and required here to show that your base is -4. We did not have to deal with that in Unit 3 because we only worked with positive bases. That has changed now. Okay. And what are we looking at here? We are not solving a linear equation. We're not solving a quadratic equation. We're solving an exponential equation. I'm going to try to write both sides as a single power of a common base. The right-hand side is 2 powers right now. Let's undo one of those factors by dividing both sides by -6. We get -16,384 equals -4 to the exponent n minus 1. Now, we've spoken when we were in class and since then about trial and error, about how it's not a great strategy. But it has also come up that once in a while it is required. It just should be an educated trial and error. We are going to solve this equation by writing both sides as a single power of a common base. You should expect, if you haven't made any mistakes here, if you haven't written anything down, that -16,384 had better be a natural power of -4. Otherwise, there won't be a natural number of terms. If I make this 305, this question doesn't have an answer anymore because there's no such term. So I really hope I wrote that number down right. Still, you can eliminate an awful lot of trial and error here when you tell me that you know that some power of -4 has to be -16,384. So don't waste your time trying even exponents here. -4 to an even exponent would be a positive power. And the time I took to discuss it, you've probably found the answer. Let's use a little bit of trial and error. -4 to the exponent 7. Shoot. Sorry, I don't intend to get it right on the first try. I usually want to show a little bit of trial and error. Well, sometimes you get lucky. We should be celebrating that I got it right on the first time. Let's pretend -4 to the exponent 5. Oh, that's too small. -4 to the exponent 9. Oh, that's too big. -4 to the exponent 7. Hey, we got it just right. Great. Now, both the left side and the right side are written as a single power of a common base. That means that the exponents must be the same. Show your reader that you're setting your exponents equal to each other. Now you've figured out how many terms there are in this sequence. The number 8 is small enough that I would be worried about how many students might just try to sort of count it out on their calculator. But I mean, I can't make the number so large, otherwise it wouldn't fit on our calculator screen either. So from here, we now have all the information we need to substitute into this formula. So let's do that. The sum of the first 8 terms of this sequence is given by a, -6, times, I'm going to square bracket that, r, curved bracket, that's my base, to the exponent 8 minus 1, all over r minus 1. Here's where I'm talking about. Maybe you just do -4 minus 1 is -5 in your head. You can try typing this in one step with a bunch of brackets, -6 times bracket -4 to the exponent 8 minus 1 divided by -4 minus 1. I'm pretty comfortable with my calculator. I've used it an awful lot, and I know what brackets I need to put in and what brackets I don't need to put in. The other thing you could do is kind of help your calculator out with the order of operations here. Start on the inside. Do -4 to the exponent 8 equals, -1 equals, times -6 equals, divided by, maybe you do this in your head, -5 equals. And there you go. What you don't want to do is have to write down what that answer was, what that answer was, what that answer was, what that answer was. You don't want to take 5 steps to do this. You should be touching your calculator once or twice in this question. Okay. Then I believe it came up in the lesson that sometimes students are surprised by this answer, and this is where the obsessive compulsive nature comes in. Instead of feeling like, oh, I've done a really well communicated solution here, students will say, this is impossible, that can't be true because I'm adding 98,304. How could my sum be less? And they erase everything. And then they say, I need more time. Where those students might not have realized that they actually had the right answer. Your sum of your first term, just a little aside here, is negative because it's -6. The sum of your first 2 terms, that's going to be -6 plus 24. That's going to be 18. Notice that that's positive, but it's less than 24. It's 6 less than 24. Sum of your first 3 terms is going to be the sum of your first 2 terms plus your third term. This is a recursive definition that hasn't really come up yet. That's going to be 18, and then I subtract 96. So that's going to be 18 larger than -96. Each term that you're adding is getting further and further away from 0, but your sum is always going to be closer to 0 than your term itself. Okay. So if you're surprised by a result, don't erase everything that you have if you're in a future class or, I don't know, post-secondary. So okay, watch out for questions like this. Sometimes students just try to jump right to the sum formula, and they get really confused when they feel like they don't have enough information. You have many different tools to use, and sometimes you need to use more than one tool. Okay, use those tools.